We're now going to look at a bunch of different examples of indefinite integrals to see if we can wrap our head around this a little bit more. So for each of these, we want to just find the indefinite integral. We're going to start with the indefinite integral of 2 dx. And I think this is a nice example of a problem that is almost so simple that it's kind of difficult. I think for this problem, to understand the solution, it's easiest to realize, okay, well, I can rewrite 2 as 2x to the 0 power. Because I know anything to the 0 power is 1. 1 times 2, that's just going to be 2. And then, okay, there's my dx. Now, if I were to apply my power rule to this guy, so, okay, we would add 1 to the power, 2x to the first power, divided by my new power of 1, and then plus my constant of integration c. We don't really need to have this 2x to the first over 1. We can just write this as 2x if we want to. But there is my indefinite integral. I think it's a little bit jarring to go straight from here to 2x. But again, check your answer here. If I take the derivative of 2x, I'm going to get back 2, which is exactly what I want. So I know that this is the correct solution. And you'll see this happen all the time in this section. Anytime we integrate just a constant, that constant just picks up a factor of x. That's the only thing that changes here. So that's one of the big differences between derivatives and integrals. And I think one of the more challenging parts of integration is very easy for me to boil it down and say, oh, well, all we're doing is adding and dividing. It's oversimplifying things. Because now you've been doing derivatives for 75% of this course, and now I'm saying, okay, now we want to do the opposite thing. You need to retrain your brain to go through this new process. So just please keep that in mind when we're integrating constants. We're not going to get an integral of 0. We pick up instead a factor of x here. All right, next I have the integral of 16 e to the t dt. This one's different for a couple of different reasons. First of all, we're integrating with respect to t, but that's really not that big of a deal. That just means we're using t in place of x. All of the same rules are all going to apply to these types of integrals. The other big different thing is the 16 right here. I say, boy, I know how to take the derivative of, say, e to the t dt or e to the x dx. I don't know what to do with this 16, though. But at the end of our last video, we said, hey, you know what? You can sort of factor out a constant multiple. If you have a constant multiple, you can factor that to the front of the integral. So I can take out that constant multiple. And I think I would recommend doing that here. 16 is a constant. It doesn't depend on t here. So I'm going to just factor that out. 16 times the indefinite integral of e to the t dt. And I think once we write it like that, it's a little bit more clear because now we can say, okay, I know what this part is. That's just e to the t. The 16 then just comes down to the next step. So I should have 16 times the indefinite integral right here. Well, we just said the indefinite integral of e to the t is e to the t. And then, of course, plus my constant of integration c. Check your answer. Hey, if I take the derivative of 16e to the t, yep, I end up with 16e to the t, so that's good. Oops. All right, let's continue on. Next up, I have the indefinite integral of 3x to the fourth power dx. Here, I'm going to pull the same exact trick that I just did earlier. I see this constant multiple of 3. You can leave it in there. You can factor it out. It's really up to you how you want to do it. If you wanted to factor that out, you would look like 3 times the indefinite integral of x to the fourth dx. And then after that, you're just using the power rule right here. So 3, I'm going to add 1 to the power, x to the fifth, divided by my new power of 5, plus my constant of integration c. The one thing I would make sure that you note here is that we're multiplying 3 and x to the 5th over 5, so that I make sure to simplify that to be 3x to the 5th over 5 plus c. However, I think when we're working with polynomials like this, I think factoring that out is a little bit more trouble than it's worth, and I think some students have some difficulty simplifying this part right here. So for polynomials, I don't know that I would recommend doing that. I would just say, you know what? We're going to do the power rule right here. We're going to add 1 to the power, so 3x to the 5th power, divide by that new power of 5, plus my constant of integration c. I think it saves you a couple steps. You don't have to worry about simplifying it. I would say there's your answer. The other way you could write your answer if you wanted to, you could say instead 3/5 times x to the 5th plus c. Either one of those is fine, and I may use them interchangeably. I may go back and forth between those two, but either one of these is going to work just fine for us. Next up, I've got the indefinite integral of 2x to the 5th minus 3x squared plus 1. Here in this case, this is new because now we have multiple terms. We're adding and subtracting these terms. So I'm going to turn again to my exponent, or excuse me, my integral rules that we talked about. We said the integral will sort of distribute over plus and minus, over addition and subtraction. So what I can do in this case is I can say, you know what, I can really take this one big integral and split it up into 3 small integrals since it's all separated by addition or subtraction. So I could rewrite this as 2x to the 5th dx minus the indefinite integral of 3x squared dx plus the indefinite integral of 1 dx, and then integrate each one of those separately. So here, antiderivative of this guy, this would be 2x to the 6th divided by my new power of 6, minus over here 3x to the 3rd divided by my new power of 3, plus here, remember this is a constant, it's going to pick up a factor of x, so this is really just plus x, and then plus my constant of integration c. And then, of course, we can simplify this, right? The 3's are going to cancel, so we've really just got plus x cubed here, minus x cubed here. 2 6, I know that that's really just 1/3. We could simplify that way. You don't have to do this, though. It might not be a bad idea when we're first starting off, when we're still kind of maybe feeling a little bit uneasy about indefinite integrals, but you are not required to do that. You can just look at this, and what we'll do once we start to get more comfortable with these is I'm just going to kind of go down the line and take the integral of each one of those 3. So I'm going to integrate this function for 2x to the 5th first. So I'll add 1 to the power, 2x to the 6th, divided by my new power of 6, minus over here 3x, add 1 to the power 3, divide by that new power of 3, plus, remember that this is 1x to the 0 power, so this will be 1x to the 1st power divided by my new power of 1, and I can't forget about my constant of integration c. Maybe I take a step just to clean this up. This is really x to the 6th over 3, minus x cubed, plus x plus c, and hey, there is my indefinite integral. So you don't necessarily need to rewrite this problem as 3 separate integrals, but if you're feeling a little bit overwhelmed with this process, if you need to slow it down a little bit, then that might not be a bad idea for you to do. Next, I've got a few more. I got a lot more actually. Next up, I've got the indefinite integral of 5 over x minus 4e to the x dx. So this one looks a little bit different. I see 5 over x, I see e to the x. There's kind of a lot going on here. Here's one where I would say I'd probably break this up. I'd probably break this up and say, you know what, this is really 5 over x dx minus the integral of 4e to the x dx. Now, this term we kind of hopefully have an idea of what to look at, because that's really similar to what we did up here in part B. So I'm actually going to pull the same trick that I did. I'm going to say, you know what, I'm just going to factor out that 4 times the indefinite integral of e to the x dx. And then I think that this part becomes a little bit more clear how to manage it. This is the piece that I think is perhaps a little bit more difficult to deal with right now, just because we haven't seen an example like this. I'm going to try and rewrite this in a way that is a little bit more workable. So you might try writing that as 5x to the minus 1 power, but let's think through what would happen then. If I add 1 to that power, it would be 5x to the 0 power divided by my new power of 0. That's not going to work for me. So I look at this, I say, hey boy, 5 over x, that looks an awful lot like this guy up here, the indefinite integral of 1 over x dx. So I want to make my 5 over x look like that. And the thing to remember is that this 5 is really just a constant multiple. When I say, and where can I do this? I'll do this right here. When I say 5 over x, I can really split that apart and say 5 over 1 times 1 over x. So if I want to, just like I did with this 4, I can take this 5 and I can factor that to the front of my integral. I can say that this is 5 times the indefinite integral of 1 over x dx. Now I think this is a lot more clear what to do with it, because I know I say, oh, that's just, when I take its antiderivative, I know that's going to be natural log of absolute value of x here, minus 4 times this antiderivative, well that's 4 times e to the x, and then plus my constant of integration c. Here we go. So for now, when we have something that's perhaps a little bit more complicated than just a polynomial, yeah, I will go ahead and split that up into multiple integrals. But for polynomials, I think it's a little bit more manageable. Next up, I've got the indefinite integral of 5 over x cubed dx. And here is where I'm going to rewrite this. When you have any other power in your denominator other than 1, so if you have 5 over x squared, 5 over x cubed, here we're going to need to do the same thing that we did when we took derivatives. We're going to want to rewrite this with a negative exponent. So rewrite this as 5x to the minus 3 dx, and then I'm going to apply my power rule again, just keeping in mind we're working with a negative exponent. Things might feel a little bit different, but we're still doing the same 2 steps. So I want to add 1 to my power, so I should have 5x to the negative 2 power divided by my new power of negative 2 plus c. And then, okay, if we want to take a second just to rewrite this, you know that I don't like negative exponents. I'm going to write this as negative 5 over 2x squared plus c, and I would say, okay, there is my antiderivative. So we will be doing quite a bit of this at first, where we need to rewrite these exponents as either negative exponents or rational exponents, depending on what our problem looks like. And speaking of, here if I look in G, here I'm integrating with respect to u. I have the indefinite integral of 4 times the 5th root of u to the 3rd du. So here in this case, once again, just like we did in the last case where we needed to rewrite that with a negative exponent, I need to rewrite this radical just like I did with derivatives. So I'm going to rewrite this. This is the indefinite integral of 4u to the 3/5 power du. So I've rewritten it. Notice I haven't added 1 to the power. I have not divided by that power. So I'm going to do that in my next step here. I should have 4. So let's add 1 to the power. This will be u. So I'm really adding 1. I want to take 3/5 plus 1. But 1, I might need a common denominator. That's the same as 5 over 5. So this will be 8 over 5 is my new power. So 4u to the 8 over 5 power. So I've added 1. I need to divide by this power, though. So I need to divide by 8/5. And boy, that just looks yucky. I don't want to deal with that. So I think about, okay, how else can I divide by a fraction? Well, we learned way back, whenever we learned how to divide by fractions, we said, hey, if you're going to divide by a fraction, the easier way to take care of that is to multiply by the reciprocal. So I'll say this a lot. Instead of dividing by 8/5, I'm going to multiply by the reciprocal, which is 5/8 here. And then, of course, can't forget about my constant of integration c. Have to add plus c there. And then after that, just simplifying this term right here. You can simplify the 4 and the 8 right now, or you can take 5 times 4. I think I'll do that. 5 times 4, this gives me 20 over 8 times u to the 8/5 power plus c, which is really equal to, there's a common factor of 4. So this would be 5 over 2 times u to the 8/5 power plus c. Hey, there we go. There is our antiderivative. So just be careful when you're working with radicals and you're working with rational exponents. You're going to, instead of dividing by that fraction, think about it as multiplying by the reciprocal. It'll make your life a whole lot easier for these problems. All right, what else? We've got h here. So here, this one's a little bit tricky. We've got x to the 4th minus 8x cubed all over x squared dx. Now notice, and I'm going to scroll back here just for a second. Notice we said, hey, this distribution over addition and subtraction, it does not work for multiplication. And I didn't actually say this, but I'm going to add it now. It does not work for division either. Does not work for multiplication or division. Think back to derivatives. We had to get the product rule and the quotient rule before we could take the derivative of either one of those. Well, I don't have a product rule or a quotient rule for, at least for integrals yet. Maybe I will later, but right now I don't. So I need to think about, well, how can I rewrite this in a way that I don't have division? And so in this case, how I want to accomplish that, I'm going to think about that as the indefinite integral of x to the 4th over x squared minus 8x cubed over x squared dx. I'm going to integrate this. So I'm just going to take each of the terms in my numerator and divide them by x squared. So before I can integrate, I need to simplify each of these two terms. So for the first term, I'll have x squared minus, over here I should have 8x dx, and now I can just integrate each of these two terms separately because they're just subtracted by or separated by a minus sign. So here I'll add 1 to the power, x cubed, divide by my new power of 3, minus over here, let's see, I'll have 8x squared over 2, that's really 4x squared, and then again plus my constant of integration c. One thing I will mention here, you can write this as x cubed over 3. You can also write this, if you prefer, as 1/3 x cubed. It doesn't really matter how you write it. I would just try and pick one and stay consistent. I'm not consistent. I don't follow my own advice. So you can write it either one, as 1/3 x cubed or x cubed over 3. Either is correct. Two more here. In part I, we've got the indefinite integral of 8 times the cubed root of x minus 6 over the square root of x dx. And here in this problem, it's going to take a little bit of rewriting. I probably want to rewrite this as 8 cubed root of x. This is really x to the first power. So I'm thinking about this as x to the 1/3 power minus, over here, first I need to take care of this square root. I know that if I have a square root, that's really x to the 1/2. So I still have x to the 1/2 in the denominator. But now I would like to take that x to the 1/2, bring it up to my numerator. So I'm going to have the integral. I'm not going to do anything right now with 8x to the 1/3. I'm just going to leave that as 8x to the 1/3 power. I think that it's confusing if you integrate this term and you don't integrate this term, and then you start, you've integrated part of it, but not another part of it. It's a really good way to get lost in a problem, so don't do that. But minus over here, I will bring x to the 1/2 up to the numerator. That'll make it 6x to the negative 1/2 dx. And now, okay, now we can go ahead and use our power rule. So 8x, I'm really adding 1, which is the same as 3 over 3. So if 3 over 3 plus 1 over 3, I'm going to have 4 over 3. And rather than divide by 4/3, I'm going to go ahead and multiply by the reciprocal of 3/4. Minus 6 over here, x, I'm going to add 1 to the power. 1, that's the same as 2 over 2. So 2 over 2 plus negative 1 over 2, I should have a positive 1 over 2. Again, rather than divide by 1/2, I say it'd be a lot easier if I multiplied by the reciprocal, this time 2 over 1. Plus my constant of integration c. And then, okay, we can simplify this. Let's see, I should have 3 times 8, that would be 24 divided by 4. That gives me 6x to the 4/3 minus 12x to the 1/2 plus c. There is my antiderivative. One last example that we have here in J, we have the indefinite integral of x squared minus 2 times the quantity x plus 3 dx. And again, I'm going to scroll back up here because I'm going to point out, hey, remember we said that we cannot distribute over multiplication. We cannot just distribute that integral sign over multiplication. So we need to take a second to rewrite this so that it doesn't involve any multiplication. I think this one's a little bit easier to see what we need to do, because think about, okay, if I was trying to simplify this, I'd probably just multiply that out. I'd go and use FOIL. So, okay, if I FOIL this out, I will have x to the 3rd plus 3x squared minus 2x minus 6 dx. And now I can just integrate each one of these terms separately. I can integrate each of the 4 terms separately. So add 1 to the power, I'll have x to the 4th divided by my new power of 4. Plus here I'm going to have, let's see, just x cubed once I'm done. As we get more and more comfortable with integration, I will start to kind of make those jumps a little bit quicker. So just I would make sure you get some practice in so that we can follow along. Here, if I add 1 to the power, divide by my power, I'd have minus x squared. And minus here, remember this is a constant. Constants will always pick up a factor of x, so minus 6x. And then, of course, I can't forget about my constant of integration c. So here is my antiderivative. Remember that you can check every single one of these by taking the derivative. So if I take the derivative of what I just found right here, I should end up with exactly what we started with. So just know that you can check your answers for every single one of these problems. So hopefully this helps you. If not, I would recommend practicing a lot of these problems. Like I said earlier, we've been doing derivatives for so long, it might be more difficult than anticipated to kind of train your brain to do this new skill. You're now you're now doing antiderivatives instead of derivatives. The process is so simple that it's easy to mix those two up. So make sure you get lots of practice with these. We're going to be working with these quite a bit here in this chapter. And in the next section, we're going to talk about, hey, how could I find out what this plus c is? What if I want to know that? And we'll talk about that in the next video.